As far as the homework goes, in particular, when you're doing things programming-wise, especially in R, I think it's great if you want to Google things for commands, because certainly trying to remember every single command is not something you're going to be doing very often anyway. Being able to refresh things, maybe learning a new command, great. Don't just chat GPT a program. If you're using something, a technique that we didn't use in class, for example, make sure I don't really care if you comment things necessarily usually, because most of the stuff that we're doing is really, really short, so it's not hard to follow. But if you're using something that's a completely different technique than what we did in class, you might want to comment so that I know that you know what you're doing. Okay. When I see something that's, say, recursively written, for example, we haven't done anything with recursion at all, you might want to tell me that you're doing that. Okay? And know why the recursion is working. So just as a general rule of thumb for programming side. Again, I expect that you're going to look things up. Absolutely. Okay. It's not like we're trying to Google a homework answer. That's different. You're Googling something to try to remember a command or seeing how a command works, or is there a command for something? Perfect. That's great. If you use a new command, just tell me what the command is. I don't really care that you're Googling that stuff at all. But don't just chat GPT something or the like, right? Because that doesn't tell me. I don't. One, some things that come out of chat GPT are wrong. They don't do it correctly. Okay. But the second piece is that, especially if you're using a completely different technique than what we're using, I'm a little suspect of that. Yep. So just, again, I'm okay with you using other techniques. Some of you have lots of programming experience and use different techniques than what we do in class. Perfect. Recursion's fancy. It's nice. It makes things short. Recursion tends to load up memory faster than iteration does. So if you got a big problem, you're probably not going to solve it with recursion just because of that. It'll probably kill your memory faster. But I don't care. It's fancy. There's some things that are really quick that you can write recursively. But just let me know that you're doing that, because I'm going to probably avoid recursion for our purposes in here. So, yeah, Braden.
Is there a due date on the extra credit stuff?
Nope.
Okay.
Nope. Well, that's not true. By the time the final exam rolls around.
Okay.
Yeah. Yeah, but all the anything that I say is extra credit, you can do at any point in the semester.
Okay.
Yeah, absolutely. And by the way, when I say extra credit, I'm going to add that into a test grade, not your homework grade. Okay. So those are extra points that you can make in your test grade. Those are the extra credit things. So I've given you a couple of different extra credit opportunities. Might do one more today. Okay? But again, you can just do that whenever. It's fine. Yep. Thank you for asking. All right. Questions on anything at all? Yeah.
On number 2 in the homework, when you have to find like the smallest and the largest value, can you go over how to like switch the exponents to different values?
So the one in the homework had 3 bits for your exponent, right? So let's just change it to a different number just so we have a different example. Is that okay? Okay. So let's say you have 4 bits for your exponent, but you reserve all zeros and all ones for the special cases of underflow to 0 and overflow to infinity. Okay. So if you have 4 bits, of course, your range is that, right? Well, in decimals, those numbers are 0 to 15. Yeah. Okay. But again, we don't want to use the all zeros and the all ones, so we really go 0 to 14, or excuse me, 1 to 14 for that, right? Because I don't want to use all zeros, so I need to bump it up 1 from the left-hand side, bump it down 1 from the right-hand side, because I don't want to use all ones.
How did you get to 15?
8 plus 4 plus 2 plus 1.
Okay.
Anything that's all ones is 1 less than the next power of 2. So we can do that quickly. So the next power of 2 would be 16. So I don't have 15. Sorry. You can do that quickly with it if you just know that's 1 less than the next power of 2. All right. So now you want to kind of divide it in half. What I mean by divide it in half is you'd like half of them to be negative and half of them to be positive. Of course, it's not perfectly half because one of them has to be a 0 power. But the easy way, most likely, is to just divide this number in half. and subtract everything shift everything by that half of a number. When you do that, we go from -6 to 7. And so those are the exponents that we can use. So these are your ranges for your exponent. So this is the biggest exponent you can use. This is the smallest exponent that you can use. And then to create the smallest number, that's when you work off the mantissa. The smallest mantissa you can have is all zeros, but there's always that understood 1 there. So the smallest we can create is 1 times 2 to the -6th, which is what, a 64th in this case? And then the largest you could do depends on how many bits you have for the mantissa. So just arbitrarily, let's say we had, I use 4 or 5, I have a 12. No, 11. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I picked 11 because if you think about how we store the numbers, 1's a sign bit, then we have the exponent bits, and then we have the mantissa bits. Usually those are powers of 2. So if I used 4, 1 more for 5 for the sign bit, 11 more, you can do a power of 2, which is 16. That's why I said 11. Okay. What's that?
Is this for number 2?
She asked me about number 2, but I just changed it to a different example. Yeah. Yeah, you're fine. Okay. So in this case, what do we have? 5, 10, 11, that was just what I said. And then we times 2 to the 7th, and then we want to convert that to decimal. 2 to the 7th would move your binary point 7 places to the right. So this would be 1, 1, 1, 1, 1, 1, 1, 1, 1 point. How many ones do I have now? 8. And then I had 12. 9, 10, 11, 12. Looks like. Assuming I got the right number of ones there. This number on the left-hand side, what do we got? 2, 4, 8, 16, 32, 64, 128, 256. So that would be 511 on the right-hand side, or the left-hand side. This is a half plus a fourth plus an eighth plus a 16th, so it's 15 16ths. So you'd have 5, 11, and 15 16ths, whatever that comes out to. What, 511.9375? I didn't remember my decimal conversion for 16th correctly. I used to have a lot more things in my head for numbers, but calculators ruined that. But that's how we do that. Okay. So when you do the smallest, it's always going to be a 1 times 2 to some negative number. And that negative is just the smallest possible exponent you can get, literally smallest in terms of negative. And then the biggest is always going to be 1 point, a whole bunch of 1s. The whole bunch of 1s is just how many bits you say you have in your mantissa, times 2 to your biggest exponent, and then convert that over to decimal.
Was the signage bit not implied?
Say it again?
Was the signage bit not implied?
What do you mean?
Like for the sign of,
Yeah, I mean, I don't know anything by implied.
because wouldn't the smallest number be -1 to the 2 to the highest?
So, but when I'm referring to the smallest piece in that case, I'm looking for the smallest magnitude number that I want. Yeah, I want the smallest magnitude in that case. It was ambiguous in that problem. But when I'm talking, you're right. The signage bit would have been implied. If I'm like thinking of the smallest in number as far as it means farthest to the left, then yeah, it would be the negative of the biggest number that you can get. You're right. So then you can just flip the sign. But when I'm talking about the smallest in terms of the absolute value, in this case, smallest magnitude thing you can get. Maybe does that help?
Yes.
Yeah. I have a question. Questions are always good.
Would you be offended if I showed up to office hours asking questions about stuff I haven't tried to do yet?
Yes. No, I wouldn't be offended. You're welcome to be. Sorry, I said the wrong word. No, I'm not offended. You can always do it. I'm horribly offended. I can't believe you'd ever ask that. Sorry, I said that backwards. You're more than welcome to go and ask about it. All right, sorry. Me trying to be welcoming and I answered it. I said the wrong thing. Sorry.
I'm a little crying about it.
Sorry, I'm sorry about that. I did just say the wrong word. That's funny. I made the wrong binary choice.
Use 0, 7, 1.
Was that?
So when you use 0, 7, 1.
Yeah, you use 0 instead of a 1, exactly. That was really funny. Unintentionally funny. Other questions at all? I don't want to offend anybody else. All right. Let's go through another example with those Lagrange cardinal polynomials like we talked about last time. And then we're going to get into another method of doing some in polynomial interpolation, which we'll use this stuff in Excel. And like I said, I think it was probably another extra credit opportunity for what we're going to do in Excel and convert it over to a programming problem. So, all right. So let's just pick out another set of data points here and see if we can figure out the Lagrange interpolation part. So let's say we have the data 0, 1, 2. This is I'm getting the data from number 9 in your book, by the way, page 175. Although I'm not doing the directions that it says to do right this second. Okay. So let's say we have the x's are 0, 1, 2, 4, 6, and the y's are 1, 9, 23, 93. Whoa, hey. 93 and 259. What degree polynomial are we going to be getting out of this to interpolate this data? 4. Good. Yeah, remember the degree is always 1 less the number of points that we have. And again, the reason behind that is if you've got a 4th degree polynomial, you really have 5 coefficients that you need to figure out. A constant one, and then your x, x squared, x cubed, and x to the 4th terms coefficients. Right? In order to be able to figure out those 5 coefficients, you need to be able to create 5 equations. And so we need 5 points to do that. So it's always going to be 1 degree less than the number of data points we have to get that particular interpolated polynomial. If you go up by degree, if you go up in degree, there might be many 5th degree polynomials that go through those points. If you've had linear algebra at all, you would have a system of 5 equations and 6 unknowns, and that's probably going to have infinitely many solutions. You're going to get free variables. If you haven't had linear algebra at all, you can ignore what I'm saying. Okay? I know some of you had it or are in it, so I would mention that. Okay? So again, if you've got more equations than unknowns, you don't have enough information to get an exact solution, a unique solution. Typically, if you don't get unique, you're probably going to get infinitely many in that case. Could get none, it could be inconsistent, but generally speaking, you're going to get more solutions. The idea behind that, of course, is you can imagine an easy example. Say you have 2 points on the x-axis. Well, there's only one line that goes through those 2 points, literally the x-axis, right? 2 points, degree 1 polynomial, or less. In this case, it'd be degree 0. Well, actually, it wouldn't have any degree, but ignore that part. There's one line that goes through. We usually think of lines as being degree 1 polynomials, right? But if I wanted to bump it up a degree and have parabolas, well, you can easily see a couple, one opening up and one opening down and going through the same points, right? You could think of x squared minus 1 going through the points 1 and negative 1, and 1 minus x squared going through the points 1 and negative 1. And then, of course, I could make things flatter or skinnier, right? I get lots of different parabolas that go through those 2 points. So if I bump up the degree, there's probably infinitely many points, infinitely many polynomials that will interpolate those points. We're looking for a unique polynomial that goes through those points, and so that's why we want the degree to be 1 less. And it may be the case that that last coefficient turns out to be coefficient turns out to be a 0. The leading term coefficient turns out to be a 0, and you actually get a smaller degree. But we're never going to go up in degree. That's what I'm trying to say. Not very eloquently. That's what I'm trying to say. Okay. All right. So degree 4. So when we're doing these Lagrange cardinal polynomials again, we're going to have those pieces that have the factors on top and the factors that look like factors on bottom. Factors on top will have the x's in them. The factors on bottom will have the numbers in them, right? So if we look at the first one, remember that we used pardon me. Oops, not a 0, a 1. We use the L sub, oh, for heaven's sake. We use the L sub I notation, right, for the Lagrange cardinal polynomials. So we've got 4 of them we're going to find, right? Okay. We want to find the first one. What do we do? Actually, I guess technically we're going to find. Sorry, we're going to find 5 of them, I guess, because we have 5 points. Sorry. There'd be 4 pieces in each of them. What?
On the tops, x minus 1, x minus 2, x minus 4, and x minus 6.
Good. So ordering it as this is x1, x2, x3, x4, x5, say, right? We want, when we plug in 0, not to get 0 out, right? But the other ones we want to get 0 out, correct? And then on bottom, what do you get?
0 minus 1, 0 minus 2, 0 minus 4, and 0 minus 6.
Good. Oops, 0. You said the right thing. I wrote the wrong thing. Remember that the top comes about because we want a 0 from when we plug in all the other points, right? The bottom comes about because we want this to be 1 when we plug in the 1 point that's not 0, right? So 0 minus 1 will cancel out the first term, the first factor. 0 minus 2 will cancel out the second factor, and so on down the line, right? That's the Lagrange cardinal polynomial. To figure out the interpolating polynomial, we'll do another step later, right? But let's find the other 2 to start with. What's going to change if we want to find the second one?
The 0 switches with 1.
Okay. So wherever I see a 1, I'm going to put a 0. Yep, okay. So we'll have x minus 0, x minus 2, 4, and 6. And then on bottom, all the zeros will all flip to 1s, and the 1 will flip to a 0. So we'll get 1 minus 0, 1 minus 2, 1 minus 4, 1 minus 6. So far, so good? Only 3 more to do. Got to do it for each point, right? Okay. So I need L3. So this, in this case, the 2 gets switched to a 1, right? So 2 minus 0, 2 minus 1, 2 minus 4, 2 minus 6. You can see where you program this not too badly, right? So the next one will be x minus 0, x minus 1, x minus 2, x minus 6, and then on bottom we'll have 4 minus 0, 4 minus 1, 4 minus 2, so 4, ugly looking 4, 4 minus 6. Last one, x minus 0, x minus 1, x minus 2, x minus 4, 6 minus 0, 6 minus 1, 6 minus 2, 6 minus 4. long-winded, right? Yeah, great.
Is there a reason we're leaving out multiplying by the y values?
Yeah, I'm just finding the cardinal polynomials first. I'm going to put the y values in this.
Okay.
Yep. Yeah, I haven't done the interpolating polynomial yet. You're exactly right.
Okay.
Yep. Yeah, these are just the cardinal polynomials. The cardinal polynomials, again, are for your data points that you have. If you plug in the data point that corresponds with the polynomial that you got, you should get a 1. If you plug in any of the other x values, you get 0. So it gives you 1 if the i's match, right? So this was x1. If I put in x1 in, I should get 1. If I put in x anything else, I get 0. And then likewise with the other one. Okay. So these special polynomials give you 0s or 1s, depending on what you plugged in for the data points that you were given. Obviously, there'll be different values for other values that you might put in. But you're exactly right, Brayden. We're not done. Yep. But are we okay with how we constructed these? Make sure we're all on the same page. Probably not going to give you something that's a 4th degree polynomial on an exam because that's a lot of writing from the same process over and over again. Right? Feels like a lot of writing for the same process over and over again. All right. But exactly like Brayden said, what do we need to do with each of these to create the interpolating polynomial now? I got to multiply by the appropriate y value, right? Now, for a 0, I don't really need to multiply it by anything because I want to get a 1 out, right? But for the second one, I don't want to get a 1 out. I want to get a 9 out. So I'm going to multiply the cardinal polynomial by the y value we want to get out in order to get the interpolating polynomial. So we'll multiply the first one by 1, second one by 9, third one by 23, fourth one by 93, fifth one by 259. Yeah. Okay. So your interpolating polynomial, which I'll denote with p of x here. Let's see if we can do this. -1 times -2 is 2, times -4 is 8, times -6 gives me positive 48. So you'd have 1/48 x.
Whoa. Sorry.
I just multiplied the numbers in the denominator. What's that? No, I just did L1s. I'm going to go one at a time. 48's just the denominator of the first one.
I'm assuming we never include x as 0.
Say that again.
I'm assuming we don't ever include x as 0. Like, because there's x value that's 0.
Yeah, that's what I used to get the first one. Right? That's where the 0 minus 1, 0 minus 2, 0 minus 4, 0 minus 6 came from.
Oh, are we only doing for L1?
Say it again.
Are we only doing like the B for L1?
That's all I did for the first one. Yeah, I'm not anywhere near done.
Oh.
Yeah, I was just simplifying L1 and multiplying it by the first y value. I'm going to do it again for the other 4. Yeah. Yep. I wasn't done yet by any stretch. Okay. Yeah. This is just the first one. Okay. The next one, we got to multiply it by a 9. Multiply out your denominator. 1 times -1 is -1. Times -3 is positive 3. Times a -5 gives me a -15. I'm going to multiply so I got a 1 over -15. I got to multiply it by a 9, right? 3's will cancel, so I get a -3/5. And that'll be times x minus 2 times x minus 4 times x minus 6.
You need to just do that like in the LT part of the note, or just like write down my notes like what you did. Because I understand what you said, I just want to make sure it's
Sure. We don't have a lot of room, but this part here is 48. So that's where this 48 is coming from. This part, so I can change the color. Green. This part here is -15. So this number right here is -9/15. Or I could write it as 1/15 and then times the 9, because that was the y value that we got. Here. Where my red was, there it was. Oops, something just happened. Oh, for heaven's sake, why are you jumping all over the place? That. Try to color code everything so we know where all the things are coming from.
How did you get the -15?
1 times -1 is -1 times -3 is +3 times -5 is -15. I'm doing the arithmetic right? Yeah. It's like I'm doing it right, yeah. 1 minus 0 is 1, 1 minus 2 is -1.
Oh. Okay.
Yeah.
I don't know why.
It's like, I'm doing that right? I didn't think I was going crazy.
I thought we were ignoring the ones.
Do it?
I thought we were ignoring the ones.
Oh, no, we actually have to compute all of the arithmetic. Yeah, we have to do all the arithmetic. Okay. We ready for the next one? Okay. Oh, yeah, I need to remind myself to do that. For heaven's sake, quit jumping. L3. Oh, so, yeah, L3 is the next one. What the heck? I don't know why we're jumping all over the place. L3 is 2 times 1 is 2 times -2 is -4 times -4 is +16. Okay. 23 is the y value. So what's the coefficient going to be out in front? Yeah, 26. Yeah, 23 16. Good. 23 is on top because that's the y value we want out. 16 is what we're dividing out, so that Lagrange cardinal polynomial is 1 when we plug in 2. Right? And we'll multiply it by the numerator here, those x's. So this will be x times x minus 1 times x minus 4 times x minus 6. Let's do the next one. 4 times 3 is 12. Times 2 is 24. Times -2 is -48. And the numerator is 93 in that case. Mine is 93. Oops. Yeah, well, that'll cancel. 31 over 16. X times x minus 1 times x minus 2 times x minus 6. And the last one was 259. So the last denominator, 6 times 5 is 30, times 4 is 120, times 2 is 240. And the top was 259. Okay. 259 over 240, x times x minus 1 times x minus 2 times x minus 4. Yeah.
Just want to make sure that's an addition sign next to the 23 over 16. Right?
Yes.
Okay.
It kind of looks like a 4, doesn't it? No, that's a plus. Okay. Phew. Is the process okay? After we got through the arithmetic?
Well, why is it 2? Did I write that down wrong?
Wasn't the last number 259?
Yeah.
Okay.
Okay.
Like, could be.
I got 6s and 9s.
All right. As long as the process is okay, we can deal with that. As long as I'm not offended again.
Are you offended?
No, I'm not. No, I answered correctly. All right. Well, that's a lot of work, isn't it? A lot of multiplications that we have to do for each one. Remember, the whole point of this was that we want to try to get a polynomial that interpolates the points more quickly, more efficiently, right? This requires a lot of multiplications every single time, and as the degree goes up, you got more multiplications you have to do. So it's not the most efficient method to use, certainly. But it does give you the fact that we have the existence of one of these interpolating polynomials, right? We know that we can find it. Now, there's a couple of things that we'll do as we go along that says, well, just because we can find it, it may not be the best way to try to interpolate the data, or maybe said better, approximate the data. We'll have some examples where the polynomial will go through the data, but it's not very helpful as an approximation tool. It's not or a modeling tool. We'll see that later. Right now, we're just trying to get the concepts down. Okay, but it does show the existence part. And since we know that if we have a polynomial of degree n, it can have at most n roots. If you have two interpolating polynomials of the same degree that interpolate the same points, well, if you subtract them, that would give you 0, and you'd end up with more roots than you would have degree, and so they can't be different. That would be the same polynomial. So we really get a unique polynomial that does this. So no matter what method that we use to get an interpolating polynomial, it's the only one that goes through of that degree. That's the whole point. Okay? So we only want just one, right? So this is one way to get it. Another way to get it would be what we talked about last time. You could set up a system of equations and solve for the coefficients, right? That's another way to do it. That one gives you literally what the coefficients are in that simplified general form, right? A0 plus a1x plus a2x squared and so on. This gives you something you would have to multiply out to get out what those coefficients are, but they should match, right? Because there's a unique polynomial that will go through these points. In this case, a unique 4th degree polynomial that goes through the 5 points. Does that make sense? In order to make sure that you have an actual honest to goodness polynomial that goes through these points, of course, it needs to be a function. We're not going to repeat x values up here. Okay. If you've done any linear regression before or doing least squares things in statistics, you know sometimes you'll get 2 y values for the same x value for your point. So if you do a scatter plot, right? In that case, you're never going to find a function that goes through all of those points because it wouldn't pass the vertical line test. So in that case, you really do find an approximating thing that goes through it. Okay. And then sometimes that's better because sometimes there's a lot of noise in your data, and maybe you try to eliminate the noise somehow by doing some approximating things. And again, like I said, we'll see sometimes that just because we can find a polynomial through the points doesn't mean we should. It's kind of a life lesson, right? Just because you can do a thing doesn't mean you should do the thing. All right, let's see if we can figure out another way to do an interpolation that might be a little bit more efficient. Okay, but this is Lagrange cardinal polynomials. This really is a way to do it. Okay. I was trying Word to write on today instead of OneNote. I'm not sure I like it any better. So I'll have a little bit more issues with things jumping around. All right, so let's see if we can find what's referred to as the Newton form. I should just write Newton form of the interpolating polynomial. All right, so here's the idea behind Newton's form. So let me go back and rewrite those data points down, making sure I write the same numbers down that I did last time. We had 0, 1, 2, 4, 6. Y was 1, 9, 23, 93, 259. Okay. Here's the idea behind the Newton form of the interpolating polynomial. And then we're going to come up with hopefully a little bit more algorithmic way to figure out what the coefficients have to be and see if we can use Excel to help us find those coefficients. That's our goal for the rest of the class time. Okay. All right. So here's the idea. The first thing we're going to do is if I ignore these last 3 points, I should be able to find a line through these two, right? Once I find a line through those two, we'll add another point and see if we can create a new polynomial off the old one and create a quadratic. Once we create the quadratic, we'll see if we can create a new polynomial and make a cubic, and then keep going in that fashion. Okay? So we'll keep adding in new things. All right, so let's start off by trying to find the line between these 2 points in a very specific way. Certainly you know how to find slope and all that good stuff, right? But let's see if we can find it in a very specific way. All right? So the first thing is that we know that if we plug in 1, we want to get out, try that again. If we plug in 0, we want to make sure we get out 1. So the first thing we definitely want to make sure we get out is a 1, right? When we put in, the first thing we want to get, the first y value we have a 1. Now, it doesn't matter what this x was, by the way. This is the first y value that we want to get out, right? So the next thing we notice is no matter what we plug in over here, whatever this term is that we're going to add on over here, when I plug in this x value, I want to make sure this thing goes away, right? Because when I plug in this x value, I want this to drop off, and I'm left with the y value that's associated with that point, right? So on the end here, I know I definitely want an x. I'm going to write it as x minus 0 to illustrate how the process works. Okay? All right? No matter what's in front there, I'll call it a constant. For the time being, I'll just call it a c. No matter what's in front there, if I plug in 0 for x now, that term goes away. I get out the y value that I want when I plug in 0, right? The idea now behind this is to figure out what do we want the c to be to make sure that when we plug in the 1, we get out the 9. Well, that just is an equation to solve, isn't it? All right? We want p of 1 to be 9. Oops. Right? In the form that we have it, I know I've got 1s and 0s and maybe things would simplify, but in the form we have it, what does that 9 have to equal if when we plug in 1, we're supposed to get out 9?
1 plus 8
Okay, so not, but I'm going to leave it as a c for the time being, right? 1 minus 0, right? I agree with you that the answer is 8, okay? But I'm being very specific about how I want to do this. It's just using the numbers, but kind of treating them as symbols rather than numbers at this point. We okay with that, though? Does that make sense? If I want 1 to come out try that again. If I want 9 to come out when 1 goes in, I better make this side, when I plug in 1, equal to 9. Right? And then solve for the c at this point, correct? I agree with you that it's 8. We'll simplify it here in a second. But let's look at the form of this when it comes out. Your c has to be 9 minus 1 over 1 minus 0. What does that look like? The slope, right? That looks like your y1 minus, I'm going to use 1s and 0s now because we're going to renumber the things when we go to the Newton's form, at least according to the textbook. Right, the Lagrange was what, 1, 2, 3, 4, 5 for the different polynomials. I could have started at 0. These do start at 0. Doesn't matter. We're just doing indices. This is f of x1, this is f of x0, or y1 minus y0 over x0, x1 minus x0. This really is your slope. So this is your constant, right? This is just the polynomial that interpolates the first 2 points, right? Okay. So let's think about how we would create the next one. I probably should have used a P1, but it doesn't matter. I'm going to use a P again. Mathematicians call that abusing the notation a lot of times. We use the same notation to mean something else. I've already read it. It's bad notation. I've already used P for something else, but just to keep using P for the next one, so I don't have to keep changing letters. Okay. All right. So let's add on the next point. So let's add on here at 2. Okay. Again, I have a polynomial that when we plug in 0, I get out 1. When I plug in 1, I get out 9. I already have that, right? Okay. The part that we want now is that I want to make sure that I get 23 when I plug in the 2. Yeah? Okay. So I already have 9 plus 8x. We've already done that part, correct? Okay. But now I need to add something else on. I don't want this to change. I don't want it to change when I put in 0, and I don't want it to change when I put in 1. But I want the appropriate number when I put in 2. Right? 2 is the next one, correct? Okay. If I don't want it to change when I put in 0 or put in 1, what quadratic term do you think we should be putting on there, not worrying about the constant yet?
Why is it 9 plus 8? Should it be 1?
Oh, jeez. Yeah. Thanks. You're right. Thanks. Sorry. Because I got 9 on the brain, because it was so we just used the last step. Try that again. When we put in 0, we get out 1. We put in 1, we get out 9. Do you agree with that now? As opposed to 9 and 17 that I had a second ago? Okay, cool. All right, try again. I want to add a quadratic term. Not worrying about what the constant part needs to be. What factors need to be in your quadratic term so that this thing doesn't change when you put in 0 or 1?
X minus 0, X minus 1.
X minus 0 and x minus 1, right? We need something. I'll call it C again because I'm already doing bad notation anyway. But if I write it that way, then I already have this is going to be 0 when I put in 0. This is going to be 0 when I put in 1. So I don't change the value of the polynomial, and I've bumped up the quadratic piece, right? Yeah. Okay. Now do the exact same thing that we just did in the previous step. What do we want to come out when we plug in 2? 23, right? Yeah. On the right-hand side, you would get 1 plus 8 times 2 plus C times 2 minus 0 times 2 minus 1. I know I've already simplified some things, but we can figure out what the C is. Pardon me. But I'm going to write it in this fashion. I'll have a 23 minus 1 minus 8 times 2, which looks a little bit weird, but I'll come back to why we're doing it that way. And then over 2 minus 0 times 2 minus 1, right? That's what your C is. You agree with that? All right, so let's think about where these pieces came from so we can see if we can recreate how we're going to get to this. Okay. So this 23 was your new function value. This 1 came about from, that was the first function value we used, right? This was our computed constant, right? And this 2 came about from where? Well, that 2 came about from those 2 pieces here, didn't it? The 2 minus the 0. We go back all the way back up here. So notice that we're getting new pieces from old. So we do have a recursive formula that works out here. We can continue doing this process over and over and over again, right? I'm not going to solve for it, but if you were doing the next part, what would it look like? If you were going to find the next one, well, we had a 1 plus 8x, right? The next number would be, what does it simplify to? 22 minus 16 is 6 over 3. Or sorry, over 2 is 3. Yeah. Right? That's what we have so far. What's the next term going to look like that you would add on that we need to solve for?
C times X minus 0, X minus 1, X minus 2.
Good. We need to create a cubic term because I want the degree to go up. So I need to create a cubic term, actually a cubic piece. It's not really a single term. We have those factors in there. But I got a cubic thing I need to add in there, right? I want to make sure that I don't add anything when I plug in the first 3 things that we did, because I worked so hard to get this to interpolate the first 3 points, right? So that's why we added the cubic, x times x minus 1 times x minus 2, because if you put in 0, 1, and 2, it doesn't change, right? And then again, you can solve for the c, and that'll be your next coefficient, and then you just keep going. All right. So this is how Newton's Newton's form of the interpolating polynomial works. Okay? You start with a line, build the quadratic, build the cubic, build the quartic, build the quintic, and keep going. Okay. All right. So let's see if we can do this a little bit more in symbols, and then let's see if we can come up with a method that will let us computationally go through and figure out each one and let Excel do it for us as opposed to us having to solve a whole crap ton of equations. Okay? All right. So let's go back to the beginning, and let's say we just had 3 points to start with. Let's say we had x naught, oops, y naught, x1, y1, x2, y2. Start there, okay? The idea here is hopefully we can come up with a formula for each of the coefficients as we start to go through, and then hopefully it will allow us to get to a general formula that we're not going to prove. We're just going to use the properties of the general formula to help us get things entered into Excel so we'll still have the numbers that we want. Okay? All right. And we can also do it by hand too, but okay, so let's see what we've got. This way? Mm-hmm. So let's see what we've got again. So we know that basically the idea here right now, we've got a polynomial that we want to fit to some constant plus some other constant times x minus x naught plus another constant times x minus x naught times x minus x1. That's what we're going for, right? That was how we built the previous polynomial. You agree? Okay. So remember, we did it a step at a time. We found this one first. Then we found the one on the linear term. Then we found the one on the quadratic term. Right? That was how we worked through it. Okay. So the first one was pretty easy to solve. The first one is what? The y naught, correct? That was the first one we got. All right, so let's go through the process now of how we found the A1. What did we do to find the A1?
y1 minus y naught over x1 minus x naught.
Good. That was the final answer, right? So what the process was, we know that we want P of x1 to be y1, right? The equation we got to solve was, this is now y naught. This is A1 times x minus x naught. And like Austin said, we can solve for A1, and we get a thing that looks like slope, right? Oops, I forgot to plug in the x1. So far, so good? Okay. So let's look at the next one. When we did the x2, we know we wanted to get out the y2. We already know the a naught is y naught. We already know that the a1 is y1 minus y naught over x1 minus x naught. And I'll have an x2 minus x naught in there. Right, because I'm putting x2 in for x now. And then the third term becomes a2 times x2 minus x naught, x minus x1. Oh, x2 minus x1, sorry. All right. Now we get to solve for A2, right? Yeah? Okay. So I need to subtract the y2 minus y naught. Oh, I need to subtract the y naught over and then this big term over, don't I? Okay. So y2 minus y naught plus y1 minus y naught over x1 minus x naught, x2 minus, minus x naught. And then I have to divide by what's here, correct? Yeah, lady.
Why don't you subtract the
Oh, I do subtract. Thank you. There. Typo. I said subtract and then I wrote that. Or right, I guess it is. In this case. Okay. So far, so good with the algebra? I mean, this is all high school algebra 1, right? Just a lot of letters. Okay. Now we're going to be a little bit fancy and rewrite this so we would see a form, and then we're going to extend that form to the next steps and not have to recreate this every single time, because that's not fun, right? Okay. The whole point of this is to get to a point where we cut down the number of commutations. This is not cutting things down right now the way we have it, right? Okay. Notice that first, if I take this x2 minus x naught here, it would get rid of this piece here, wouldn't it? Okay. I'm going to move this up here. Yeah, that's right. Okay. So I'm going to move this up, and so you have a y2 minus y naught over x2 minus x naught there. Make sure I'm getting all my symbols in the right spots. And then it will have, do you want to do it that way? Nope, I don't want to do it that way. Hold on. Sorry. No, it's okay. I want that piece to go away. Yeah, okay. Let me just back up for a sec. Sorry. All right. So I want to see something different here than what I have to try to get things to match up with a particular form. So I want to play around with, I'm going to move this term up to start with. I'm going to move this piece up. I'm going to write it as y2 minus y naught over x2 minus x1. And then minus the y1, I'm going to write it this way. That way. All right. One of the reasons why, I'm going to simplify the top where it looks a little bit nicer. But one of the reasons why I have this written as the x2 minus the x naught on bottom is if I compare it back to the A1, which I'm not going to scroll up to get since I don't want you to have to scroll back up or watch me scroll while you're trying to write down. The piece that was the A1 before was this part, right? Notice on the bottom of the A1 is an x1 minus an x naught. What's on the bottom of the A2? An x2 minus an x naught, right? And if you continue this process, the bottom is going to end up being x wherever you are, 3, 4, 5, minus x naught on the bottom. Okay? That number, the x naught will stay the same. This number is going to change and go up each time. Okay? That's the reason why I wanted to leave this in here. Oh, the top is gross, I agree. Right? Okay. But let's see if we can play around a little bit with it. I'm going to do it off to the sides, the side here. See if I can. Did not do this very well because when I hit, can I select that? Nope, sure can't. Okay. Okay, cool. I did get an extra page in there. Excellent. All right. I want to try to get a common denominator up on top and see what simplifies. Okay. All right. So, if I do that in this case, okay. Yeah, because I want things to flip around. Let's multiply this one by the x1 minus x naught and see what happens. I'm going to do this off to the side. So that basically, I'm trying to get this back to a form that we see what's going to happen. So I would have y2 minus y naught times, I have to multiply the first one by x1 minus x naught, correct? I'm only working with the top. I'm not writing it over the bottom for the time being. Okay? Okay. Let's see if there's some pieces that we can cancel. That's the idea here. And then refactor some things, hopefully. Okay. All right. Notice that we get what happens here. I've got a y naught, x naught here that's added together, right? And I've got a, I don't know why that disappeared. Oh, it's probably because I'm in between pages. Okay. I've got a y naught, x naught here that's a positive. I've got a y naught, x naught here that's positive, but I'm subtracting the two things. So those two terms are going to go away. Agreed? Okay. What else do we have? Just thinking about the things that survive. I've got a y2, x1 here. I've got a y2, x naught here. That's a minus. I've got a y naught, x1 that is also a minus. And then we said the last term went away, right? So I'm just foiling there. Y2, x1, y2, x naught, minus. Y naught, x1, minus. And then the last terms went away. The other one, we've got a y1, x2. That's a minus because there's a minus out in front, right? Pardon me. This is not going to refactor nicely. This is not the way I did it before. I practiced this, so bear with me. Y1 x naught, that's going to be a plus. I've got a y naught x2, that's also a plus. Is this okay? From the algebra perspective, I know it's not pretty. Just go, I'm only going to do this once. I'm not going to expect you to reproduce it. Just showing you where it comes from so that we can recognize the pattern. Okay? All right. So let's see what kind of things we can combine-ish. All right. So let's see here. I've got a y2, x1. And I've got a y2, x naught. If I factor off the y2 out of that, I guess I could have just left it like that because I just multiplied it out. That was dumb. Sorry. It's okay. Over here, notice on the right-hand side, where do I see the x1 minus x naught again with a y1? I'm looking for a y1 here with an x 1. I'm looking for a y1 with an x1. Because I thought I was looking for a y1 with an x1. Oh, hey. Why does it do that? Seriously, why does it do that? Yeah, I guess they're okay. So what am I know what I'm trying to get to. Why am I seeing this wrong? Oh yeah, there's not gonna be an x1 minus x naught there. Y2. Oh, goodness gracious. As I said, I didn't do this the same way that I did it in my office, and now I'm getting lost in the algebra. You know what? We're going to stop the algebra, and we're just going to write down what the result is because that's all I really care about anyway. All right. This will simplify to this. I'm just not seeing what I need to get to here because I'm not doing it the same way I did in my office. It's just dumb. All right. On top, you should end up with a y2 minus y1 over x2 minus x1 minus a y1 minus y0 over an x1 minus x naught over x2 minus x naught. That's what you should end up with when you're done. I promise. It's just a matter of getting things rearranged and refactored out. I hate when I do that. All right. The whole reason I wanted to go through that was so that you can see the patterns and we don't have to go through it again. Okay? Again, notice on bottom you've got x2 minus x naught. When you're finding your next one, you're going to have an x3 minus x naught. Notice up here, you've got differences in the middle. Right? I've got y2, y1, x2, x1, y1, x naught, x1, x naught, and subtracted. Okay? The name they give for this is what's referred to as divided differences. Because we're dividing differences. Okay? So we're doing what are referred to as divided differences. I'm sorry I messed that up. I'm not going to, again, I wasn't going to make you ever redo it. I just wanted to show you where it came from so that we can recognize the pattern. And I flubbed it up. It happens. I've only done it 3 times in my office, but come to class, get it stuck in a different way and screw it up. It's fine. Whatever. All right. So this is a divided difference. Here's the notation for your divided differences. So for the first one, that A naught, we just write with brackets. With the brackets are meaning our divided differences notation. Okay. Your A1, we would write as F bracket X naught X1. And then so on up the line. Your A2 will be X naught, X1, X2. The way you find it, what did we do? Well, we did the difference of X2 to X1 and minus the difference from X1 to X2, or X1 to X naught, I mean. So the formula is F of X2, X1, or 1, 2. I'm running it backwards, sorry. X1, X2 minus X naught, X1 over X2 minus X naught. That was what we did. We compute this divided difference just like we would compute this divided difference. We're just doing it from a different set of points, right? This one was computed from the first 2 points. This will be computed from the second 2 points. Okay? So likewise, when you get to the higher ones, if you want to do X naught, X1, X2, X3, you're going to do, pardon me, a similar thing. You'll do F of X1, X2, X3 minus X naught, X1, X2. And then this will be X3 minus X naught. At any given point, you're going to be doing previous divided differences to get at these things. And again, this notation just means you're doing this for the second, third, fourth point, and this is for the first, second, third point. We started counting at 0 with this. All right. So let's see how we go through this algorithmically with a table, and then see if we can get into Excel in the next 8 minutes. The clock just changed. Next 8 minutes. Okay? So actually compute it. All right, back to the data. I'm going to write it vertically this time. Your x's were 0, 1, 2, 4, 6, right? And your y's were 1, 9, 23. 23? Is that right? 93, 259? Okay. All right, so your book just says, oh, I should have left a bigger space. That's okay. F bracket with a comma in the middle to start with. So this one actually, they use an F bracket here as the notation. Just that you're doing that first set of divided differences. Okay? So here's the algorithm. In the first case, I'm working off of these two. So I'll work off of those two x values. 9 minus 1, 1 minus 0 gives me 8 here. Right? These two, those two. Gives me the 8. You're dividing, right? 9 minus 1, 1 minus 0. Okay? Here, 23 minus 9, 2 minus 1. So 14 minus 1 is 14, right? 23 minus 9 is 14. Okay. So again, it's coming from the 23 minus 9 and the 2 minus 1. The next one's going to be 70 over 2. So 35. The next one will be, oh goodness gracious, 166 over 2. All right. Say 83. Yeah. Okay. So notice when we were doing this example before, the 1 and the 8 matched. That's what we had before, correct? Okay. See if we can get the next one to match and see if I screw this one up or not. All right. We're doing the next set of divided differences. So your book is labeling that way. Just so you know you're on the third one here. Okay. All right. Again, divided differences. You're going to take the difference of consecutive ones, right? 14 minus 8 gives me 6. But I have to go with the x values that are 2 apart now. That's the x2 minus x naught there, right? I have to go with the ones that are 2 apart. So 14 minus 8 is 6. Divided by 2 gives me 3. Did we get 3 before? Oh, I think we got, yeah, cool. Good. It matches. Wonderful. Okay, what's the next one? How are we going to compute the next one? Fantastic. 35 minus 14. We're in the second column, so I have to go back to here, right? So this is x2 minus x naught. The next one would be x3 minus x1, right? Okay. So what is that? 19 minus 3? Oh, so it is 21 minus, it's 21 over 3. Thank you. 7? Okay. The next one, what are you going to do? Good. Yep. 83 minus the 35. 48. Over 4. So we get 12. So far, so good? Probably not going to get into Excel today. We'll do that on, well, you can probably think about how to get into Excel. But at least you can get these things computed now with a table, right? Okay. Now, what's the next one going to be?
7 minus 3. 4 minus 0.
Good. 7 minus 3. Now we have to go back 3 spots. 4 minus 0. So you just get 1. The next one's going to be, yep, 12 minus 7 over 6 minus 1, all the way back. Right? Get 1 again. Which you can probably figure out what the next one is. Yeah. Yeah, it should be 0 over 6. 1 minus 1 gives me 0 over the 6 minus 0, right? So again, the very, very last one, you have to go this way. Okay. Now the coefficients you're looking for, we have this whole long table to give us the coefficients, but the coefficients you're looking for are down that diagonal. Those are the coefficients for your Newton polynomial. So your p of x will be 1 plus 8x, that's the x minus 0, just like we did before, right? The next one will be plus 3 times x minus 1. X minus x. Oh, no. X minus 0 times x minus 1. What will the next term be? Good. And the last coefficient is a 0, so this really is a cubic polynomial instead of a quartic polynomial. But the last one, if we had a coefficient there, what would your factors be multiplied by? Good. Be x times x minus 1 times x minus 2 times x minus 4. It's just times the 0 in this case. Okay. That's how divided differences work. Let's bump your homework that you do on Thursday, so we have time to practice more of these, get something in Excel so you can see the Excel form of it. Okay? We'll bump it back to Thursday. Probably would have got done today if I, hadn't screwed up the algebra. It's okay. All right. One big thing about this, notice that we started off at 0 and worked from there. But we could have started from any point and reordered any other order we wanted to do, right? We wouldn't have to start from 0. So for example, if you had this data and you wanted to approximate something like f of 2.8, now 2.8 is not a good example, 2.4, what point would you think you would have started off of first? Rather than the 0, the 2, right? If you wanted to estimate, use this idea and estimate 5.7, what number do you think you would have used first? The 6, right? You're going to use something closer to what you're trying to estimate from to do your interpolation. Again, the order doesn't matter because there's a unique polynomial that goes through all the points, right? So if you're trying to estimate something based on that data, you want to be smart and pick something to start with that's close, right? Kind of like when you were trying to do approximations with derivatives, right? You want to pick a derivative at a point that you're close, that you know the derivative of, that you're close by to, and use that tangent line approximation to approximate. Same concept. Okay? All right, we'll do more examples of this next time. I apologize again for the algebra flub. It happens. Yeah, I'm not. It happens. Have a good one.